Dr. Murthy, do classification problems like regression problems have matrix representations?
If you look at it, even this one is a nice matrix multiplication. Again, let me think about weights W2, W4, K1, K2, K3, K4. Okay. H1, H2, H3, H4. Okay. So I can now write it as W1, W2, W3. This is W1, W2, W3, W4, K1, K2, K3, K4, H1, H2, H3, H4. And now this is a 3 by 4 matrix. Now my inputs are 4 by 1. Let me first put some kind of a matrix enclosure here. This is called weight matrix. And now I have my input, which is my x1, x2, x3, x4. x1, x2, x3, x4. Okay, I should have done b1, b2, b3. Well, b1, b2, b3 I should have, and I should have a 1 here. It's obvious. So let's just don't punish me for not doing that. But in reality, this is, I will add a b1, b2, b3. I'll add a 1 here. So, but the point here is, as you can see, w1 x1 plus w2 x2 plus w3 x3 plus w4 x4 is equal to y1 is equal to, again, y1, y2, y3. K1 x1 plus K2 x2 plus K3 x3 plus K4 x4 plus 1 times b2, let's say b2, h1 x1 plus h2 x2 plus h3 x3 plus h4 x4 plus the bias term is y1, y2, y3. So this is, as I said, both network representation and graph representation are absolutely equivalent of each other. So this nice graph, I think this is very nice, sweet and easy to understand. And this is easy to code because it's a matrix multiplication. Both are absolutely equivalent of each other. Okay. So those of you who are, the reason why I'm not writing is because maybe I think it's easy enough. B1, B2, B3. Try to align it. And that's a bit difficult. Let me just write A1 here. Okay. So now you know matrix multiplication. So this is a 3 by 5 matrix. This is a 5 by 1 matrix. When I multiply, I get a 3 by 1. By the way, those of you who know a lot of neural networks, please don't get upset that I'm representing this the way I represented here. When I get into more complex networks, I will get into more standard notation. But for the time being, this is easy enough to understand.
Thanks for that handy matrix representation of classification problems, Dr. Murthy.